So now let's move on to some examples. Okay, so the first example is the problem that we've already looked at so far. According to early polls, candidate A was supposed to win 63% of the votes, and B was supposed to win 37%. When the votes were counted, A won 340 votes, while B won 166 votes. One of the things that I like to do just to help myself is when I think of the null hypothesis, right? When I think of the null hypothesis, I sort of write it in a sentence that the proportions of votes, right, that's my population, should be like predicted proportions. Proportions. Okay. And the alternative is that at least one of the proportions of votes will not be like predicted population. What I also like to do is I like to sort of draw this out for myself. I like to draw out the predicted population. So I'll color candidate A in blue, and so that will be about 63%. And candidate B will be in red, and that'll be 37%. And so eventually I want to know whether this is reflected in my actual votes. The significance level, we could set it at 0.05 just out of convention, and we know that it has to be one-tailed because this is definitely going to be a chi-square. And we know it's a chi-square because it's about expected proportions, right? So now let's set our decision stage. Now our decision stage, it's helpful to draw that chi-square distribution and to sort of label it and put our alpha here. And this is our rejection region, 0.05. Now it would be nice to know what our critical chi-square is. And in order to find that, we need degrees of freedom. And degrees of freedom is the number of categories. So in this case, 2 minus 1. And that's 1 degree of freedom. And it's because if you know, let's say, that candidate B is supposed to win 37% of the votes, you could actually figure out candidate A, right? Like you don't need me to tell you what that is. You could figure it out. And candidate A cannot vary, the proportion cannot vary freely once you know this one. And that's why it's number of categories minus 1. All right, so now that we have that, it might be useful to look at either in the back of your book or use an Excel spreadsheet, Excel function, in order to find our critical chi-square. So in order to find chi-square, there are two functions that you need to know, just like tdist and tinv, fdist and finv. Now there's chi-dist, right? Actually, we need to use chi-inv right now because here we have the probability, 0.05, and the degrees of freedom, 1. And that will give us our critical chi-square, and that's 3.84. So critical, and so this is the boundary we're looking for, 3.84. So anything more extreme, more positive than 3.84, and we're going to reject our null hypothesis. All right, so now that our decision stage is set, now it's helpful to actually work with our population. And remember, when we talk about our population, I should have left myself some room. When we talk about our actual sample, here's what we end up having. We have our observed frequencies already. So for candidate A, I'm going to write a column for observed. and candidate B. So candidate A, we observed 340 votes. So that is our observed frequency. For candidate B, we see 166 votes. Now, one thing that helps is if we know what the total number of votes was. So the total number of votes is going to be 340 plus 166, and that's 506. So 506 people actually voted in this thing. So down here, I'm going to write total, 506. Now the question is, what should our expected frequencies have been? So here I'm going to write expected. And I know that my proportion of expected should be 63%. That means if this is the total number of people who voted, so here's our little sample of 506 people, right? This is our 100%. But here we have 506 people in our sample. We should expect 63% of 506 to have voted for A, right? And so how do we find that? Well, we're going to multiply 63% to 506 to find out how many votes that little blue bit is, right? And so that's going to be 0.63 times 506, that total amount. See, if we multiply 506 by 1, we would get 506, right? So if we multiply it by a little bit of a smaller proportion, then we get just that chunk. 318.78. Actually, I am going to put this here. Let me actually draw this little table right in here, because that's going to help us do our find our chi-square much more quickly. And so observed, expected frequency. Observed frequency is 340 and 166. Okay, so what is our other expected frequency for B? So in order to find this little bit, we're going to multiply 0.37 times 506. So 0.37 times 506. And that's 187.22. And usually, if you add this entire column up, you should get roughly a similar total. When you do it, when you do these by hand, sometimes you may not get exactly the same number. It might be off by just a little bit because of a rounding error, right? Because if you round to the nearest tenth or you round to the nearest integer, you might get a little bit of a rounding error, but you shouldn't be off by much. So that's one way you could check to see what you did was right. And so once we have this, so let me just copy these down right here. So 318.78 and 187.22, right? And for each of these, the total is 506. So here, one of the things we see is that the expected values for A are a little bit lower, and the expected values for B are a little bit higher, right? But is this difference in proportions, is that significant? Is that standing out enough, right? And in order to find that, we need to find the chi-square, the sample's chi-square. Now, I've completely run out of room here, but I'll just write the chi-square formula up here. So the chi-square is going to be the sum over all the categories of the observed frequency minus the expected squared as a proportion of the expected frequencies, right? And so what I'm going to do is calculate this for each category, A and B, and then add them up. So right here, I'm going to call this a column O minus E squared all over E. So I'm going to do that for A and B, and then sum them up. So my observed minus expected squared, all divided by expected. And so here I get this proportion, and I'm just going to copy and paste that down here. And then here I'm just going to sum them up. And I get 3.817. Ooh, we're really close, but no cigar. So we're right underneath. So our sample chi-square is just a smidge smaller than our critical chi-square. So here we're not rejecting the null. We are going to fail to reject the null. So let's find the p-value. So in order to find the p-value, you could use chi-dist, or alternatively, look it up in the back of your book. Look for the chi-square distribution. It should be behind your normal, your t, your f, and then chi-square should come right behind it, right? So usually it goes in that order. Maybe it's slightly different order. And our degrees of freedom remain the same, 1. And so, our p-value is just over 0.05. It's 0.05, if we round, 0.051, right? So because of that, we are not going to reject the null. So we're going to say, hey, the proportions of votes are roughly similar to the predicted proportions. Well, they're not significantly different, at least. They're not super similar, but we can't make a decision about that. But we can say they're not that different from this. They're not extremely different, at least. Ta-da. Okay.